So, good evening, everyone. Thank you so much for joining here. My name is Yousry, and I'll be talking today about Delta Lake, a little bit under the hood. So, you know, the current age, everything now is pretty much large language models, DALL-E, whatever, big data. I know, yes, we can have some 1 million, 10 million, whatever, in memory, but eventually sometimes you need to have a little bit more capacity, storage, and compute to proceed with your workloads. So Delta originally came from the idea of, maybe I mentioned the agenda quickly. We'll go through some fundamentals about maybe what Delta looks like just without Spark, plain Delta set as a protocol. And then we'll talk about concurrency. If you have multiple processes or jobs or data factory pipelines or whatever, trying to write or read from the same table at the same time, we'll have a look at optimizations, and there will be a small summary. So Delta came from the idea that having a cluster running 24/7 or whatever, I mean, or having a cluster just to have your data available, something like a Hadoop cluster is very expensive. So they wanted to decouple the storage from the compute. And the most cheap type of storage right now is the cloud storage, like an object storage, S3 or Azure Blob Storage. Okay, but Parquet, I mean, Parquet as Parquet is not really enough. It's very fast, it's columnar, but you don't have things like asset transactions. You cannot have multiple jobs or whatever. Disconnected for something. You cannot have stuff running concurrent jobs trying to read and write from the same table, otherwise there will be corruption. I remember at some time in Telstra Purple, we were kind of processing 300 gigs per day, and eventually, if something has to be fixed, you need to rewrite the whole thing once again. The whole parquet table has to be rewritten. But Delta will allow you to, like, what? Okay, I have one record out of 1 billion broken. I can just fix that one only. I don't have to rewrite everything. Okay, so we'll just discuss some fundamentals about Delta first, what it looks like. I think if some of you have used it, maybe you have seen this kind of demos or presentations from Databricks and whatever. There is quite a bunch of Parquet files, and the transaction log folder looks to this. We need to fix something here or what. It's going on and off all the time, and I think it will be very annoying. I can do something in the background, but just to give you a quick idea, a bunch of Parquet files, plus a folder called underscore transaction log, containing a group of JSON files that will contain information about commits to that table. Okay, and by the way, Delta is not really, it's kind of related to Databricks and Spark or whatever, but you can use it pretty much anywhere, even without Spark. So you can find it on stuff like Synapse. You can find it on I think Athena right now, on ADLS, on premises. You can even read and write to Delta without Spark completely. There is a Rust binding, so you don't have to have Spark. You can write an Azure function or an AWS Lambda, write your code in Rust or Python, and it will just work. So there is no hard dependency on Spark or Databricks, and I think I'm having a bad time today.
If I could make a suggestion, it could be the refresh rate or the display settings on your Mac. So it might just
try another USB-C port.
Yep. Okay.
Oh no, it's got a HDMI switcher at the back of it.
HDMI.
Yeah. How many engineers does it take to fix a HDMI cable?
That's great.
I'm sure we can get some good data out of that.
Working like 2 hours ago. Okay.
4K too. Here we go.
I'm fine with the back colors, no big deal. Okay. Yeah. Cool. Remove this one. All right. So we'll discuss now. I mentioned that yes, you can use Delta in your workloads even without Spark if you want. So let's discuss how to build a Delta Lake, just plain Python. Okay, Delta Lake table. All right. So I will not run the code. It's already like what I think executed some time ago, but I'll just explain. So initially, you need to write a bunch of some JSON inside the transaction log. And Delta itself is open source. There is a protocol that is open source. You can go and have a look on the repo, and there is everything you need to know about Delta is found in this kind of markdown file, Delta transaction log protocol. Some specs here and there, and certain actions, adding a file to the table or removing a file, a parquet file, I mean. So we need to have some JSON documents, and I'm just writing them as what a Python dictionary. You need to define your schema. Okay, so a table will have columns and data types and so on. A bunch of other things like table ID and stuff like that, and creation date. But the important thing here is that we'll have something called provider. So Delta is pretty much parquet, but because these are most commonly used format for everyone pretty much. But you can even use stuff like JSON if you want. The underlying data file can be JSON or can be ORC. So, but we'll find parquet everywhere, just to mention. Okay, have a small function to create take a pandas data frame and write it as a parquet file, okay? So let's create an empty table. So an empty table is just that protocol string plus the metadata like the columns and whatever, write them to a JSON file, and that's it. Just go try to read the data from that. This is a table folder, throw a JSON file in that transaction log folder, and then you will get an empty table. Okay, sounds good, easy. So I'm not using any kind of Delta library on a Spark or Python or whatever. It's kind of plain Python right now, just to understand how it works behind the scenes. Okay, cool. Let's write some data. So I'll write a parquet file containing two records, first and second, as names, and 1 and 2 as IDs, whatever. I'll call it file 1. You can call it anything. So our transaction log will contain JSON that is what looks like this one, and add action, add protocol action. So our table will contain one parquet file called file 1, whatever, and you need to provide the size. You can provide additional metadata, but I'll come to that later. Write that JSON content to the next. They are kind of coming in sequence. That transaction log commits come in sequence 0, 1, 2, and so on. Write the file itself. So we wrote the file, the parquet file, and the table path itself, and we wrote the next commit file or the transaction log file, and then you'll get your data. So this is effectively, the table I created kind of manually is completely acceptable by Databricks or any other Delta capable consumer or reader. Okay, cool. What next? Let's update data. This is one of the exciting features about Delta itself. You can update the data there. It has ACID transaction. It is not immutable like a parquet table or whatever. Okay, so in our case here, we have our data in a single file, and I'd like to, for example, update the second record to have a modified name or description or whatever. So this means the whole file has to be rewritten. You cannot just extract one record and put it in another file or whatever. What will happen when you update data in Delta table? Whatever tool you are using, like Databricks or whatever, we need to scan the existing table, find out the records that are to be modified, and then rewrite all the files hosting such records, even if it will rewrite the whole table. So sometimes you might be modifying just a few records, and eventually you'll find that the whole table will have to be rewritten. And there are some ways to make that better. But anyway, so for now, I'll update one record which lives in the same file. So I'll create another file called file2.parquet. I'll add it. We have an add action here, adding file2.parquet. And I have to remove file 1. So file 2 has a previous record as it is, and then the updated record. So there's another remove action to remove file 1. I write the parquet file path, or file 2 only, and write the transaction log number 2, and load the table. We'll see that second record has been updated. So this is how updates are done behind the scenes in Delta tables. All right? Cool. So if we enumerate or display the files inside that Delta table folder, you will find that there is file 1, file 2, and Delta log, meaning that if some file is not needed or contains deleted data or whatever, it will be still there. And you need to think about it from at least a storage cost perspective, okay? But And this is what they call tombstone file, all right? Actually, this is the idea of this is how Delta itself allows you to do time travel, because updated or remove data or whatever is not really hard to remove. It is just soft removed or mark it as deleted, just mark it as deleted. So you can go inspect or read the same file as of a previous version or a timestamp, and eventually you'll get the previous data. So nothing is lost, really. Everything is still on cloud storage. Sounds good. Okay, cool. What will happen if we throw another dummy file in the folder? I'm just creating a dummy file and just dropping it into the folder, which is our friend here, okay? And that parquet file contains data. Will it impact anything in the table or not? Really? Let's have a look. Nothing will happen. I mean, even if you throw like 100 parquet files over there and try to read the data table, everything will be still the same. Nothing will be impacted. Because you can imagine like when there is a big job running or whatever from Databricks, Spark, whatever, Synapse, when it writes to Delta table, it will write first parquet files and then try to commit the transaction using the JSON file. So if the job is kind of broken for any reason or something happens or whatever before the file is committed, such files should not impact the data in the table. They act like rubbish files or data inside the folder itself. If you consume data from the table, nothing will be really impacted. So you can see that, yes, we dropped some dummy file there, but the data is still the same. And whether you have like very old data deleted or updated long time ago, or you have this kind of crap data or files coming from incomplete transactions or whatever, you can vacuum that. Vacuuming meaning like deleting any files that are not active. Okay, so just for saving you the storage cost, but take care, don't vacuum aggressively like this one, otherwise you will lose stuff like options to time travel and so on. Okay, so if we vacuum right now, run the vacuum command, you will see that the parquet table contains a log folder and file 2, because file 2 is the only active file. Everything else that is a logically removed file or any other kind of rubbish data will disappear, okay? But this means that if you try to go and time travel, you can see now after vacuuming, we still have the same value data. And I'll try to scroll quickly here because there might be some S3, I don't know, locations and this kind of secrets or whatever, which might be confidential, I don't think so, but anyway, if you try to time travel to the previous version, which was requiring file 1 to parquet, you will get boom, file blah 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 is not there, cannot really do the time travel because the parquet file relevant to that version does not exist anymore, okay? And you can inspect, I mean, this is part of the asset transaction functionality or whatever, you can inspect all these kind of transactions. Practically, if you are on a platform like or running your stuff using Spark or Synapse or whatever, you'll find some metadata coming here and there and so on. But yeah, because I'm doing stuff manually now, you'll find lots of that. Okay. So, another idea here, because I'd like to go and move on quickly to the next topic, is that you can imagine that if you have a streaming workload or whatever, and the stream runs every few minutes, writes a bunch of parquet files, 10 files or whatever, every 5 minutes or stuff like that. After a week or month, you will find millions of transactions accumulating inside that data table. And you might think, okay, so reading from that data table will require Spark or whatever tool to go enumerate all the files, JSON files from the transaction log. That will be super slow. So from the Delta protocols, they have an optimization mechanism. It doesn't have to be implemented, but it's there. They come every 10 transactions or whatever and accumulate all the add and remove file actions into a small parquet file. They call it the checkpoint. And there is a config file to control how many transactions you would like to create the checkpoint after. So I'm just creating lots of files here, writing lots of files. So we see, okay, how many here? Maybe hundreds of JSON files, and it will be really ugly to enumerate them and try to come up with a list of active files and so on. So there is an option such that, but you have to use a Spark thing. So I'm just using Spark to insert into that table, and Spark will detect, okay, I have lots of JSON files and there is no checkpoint yet, so I'll create a checkpoint for you. So after a while, you'll go and, sorry, oops. also, oh, come on. There will be some file over there called checkpoint file. You can see here. It will be a parquet file. It's not data, it's just metadata, like what are the active and removed files in the current table. So it will speed up your queries. So make sure if you find some queries like what's slow or whatever, maybe someone has set that config parameter to a bad value, like 1,000 or whatever. Anyway, one additional idea here related to having lots of small parquet files, and I think some of you might have heard about the idea of tiny files problem. Okay, so Delta has an option or a command such that if you have lots of small files, it can consolidate them for you into a single parquet file. There will be compression and it will be much more faster. So yeah, I mean, you can run the optimize command, and we'll come to optimize later when we talk about that order. And optimize you can see that it has removed like 500 files. We had originally 500 parquet files with maybe a record or two in each one of them. But once you run optimize, it will produce a single parquet file, and everything else will be logically removed and stuff like that, which will make your queries much more faster. So this is pretty much Delta basics without any tool or whatever. You can just write it using Python, C++, whatever. Actually, there is a Rust binding. You can use Rust, and if Rust is a little bit more complicated, there is a Python binding on top of that. So you can just read and write from Delta, completely outside Spark and Databricks. You can do it on your machine or anywhere in the cloud or whatever. So first part, sorry, I mean, we'll try to be quicker later. But is there any questions on that part, in the fundamentals?
On the part about ACID transactions, were you specifically committing or rollbacking when you're
I'll come to that into the next section. Okay, cool. This will happen here related to concurrency. So Delta is built on some protocol or some concept called optimistic concurrency. As I mentioned, Delta cannot be really used like an OLTP database. Some people think, okay, it looks like SQL Server. I'll just use it like a backend for my web application. No, that's a bad idea. So they have an option called, or the concept behind the locking mechanism here is called optimistic concurrency, meaning like most of the time there will be only a single writer to the table. And that's why they are able to host such Delta tables on cloud storage. On AWS and Azure, there is an API called put if absent, meaning like what? Put that kind of JSON file if it doesn't exist. And if it exists, there will be an error and you need to retry your transaction, whatever. So yeah, this comes like what? There is a white paper explaining that concept, but on AWS, there is a big problem because you don't have such API. So if you have Delta, kind of open source, not on Databricks will handle it for you. If you have Delta, like EMR or whatever on AWS, you need to plug in DynamoDB as some sort of locking provider. It's a little bit complicated concept, but the idea is that to have the concept of asset transaction, you need to write that transaction log file, the JSON file. And AWS and Azure and GCP, they have the API to like what, create the file if it doesn't exist. But if someone else created the file before you, your call to create the JSON file will fail, and your library will know you can retry manually or whatever. Okay? So in this case, I'll show you, or this example, I'll show you what will happen when we have multiple like what jobs writing to the same table concurrently. Maybe you have lots of Azure Data Factory pipelines and they are overlapping in time and happening to write into the same table. What will happen? Okay. So what I'll do here, I'll have an initial. I'll create I've got 3 tables. The first table, all of them they look the same pretty much, an ID and a bunch of dummy data. Okay. So we'll have table 1, table 2, table 3. I'll take table 1 initially. And I have some Python plumbing to do parallel stuff, running stuff in parallel, okay? And then the first example here is trying to have four kind of jobs or threads writing to the same table concurrently, but writing here in append mode, okay? So all of them, like what? Let's assume that you have multiple Lambda functions receiving files from AWS or from somewhere, and all of them trying just to append streaming or pulling from Kafka or whatever, okay? So what will happen if all of them are trying to append at the same time? The good thing about this scenario is that there's a scenario that is they call a blind append, because your operation does not depend on anything else. You can just throw a parquet file for your data and put a JSON file for the transaction log. And if your sequence number has been taken, you can take the next one, and stuff like that. So you can see here that this process works fine, nothing is broken. I'll show you something else here. That has a nice feature, which is with every transaction, you can put a little bit of message containing some metadata or some correlation identifier, transaction ID, or whatever. So here I'm putting stuff like what this commit coming from task 1, 2, 3, whatever. Okay. So let's have a look at that one. You can see now. I didn't really mention, but that table is a million records table. Okay. And what I'm doing right now, I'm trying to write 10,000 records from 4 jobs in parallel, so every one of them writing 10K. So eventually your table will be 1,040K. That makes sense? Let's have a look at the history. This was the initial transaction. You can see now lots of metadata coming from Databricks. This was the initial transaction for creating the table itself, the million records. And then you'll find 4 transactions here, 4 write operations. All of them will be marked as something called blind append, which is completely fine if you have stuff running in parallel. And the nice thing here, you can see that actually they are task 1 committed first, and then 2, and then 3, and then 1. You can see that they haven't not really on the chronological order. So yes, completely fine to have stuff running in parallel and nothing will be broken. You will be trying to commit, and if one of them trying to commit version 3, and meanwhile someone else but committed 3 before that, it will just go for version 4 and so on. So pretty much handled for you behind the scenes blind appends. What will happen with something like a little bit more complicated? The next one, we have the table number 2, similar table, creating table number 2. Okay. Next one will be a little bit more complicated. We are doing, where is that? A merge. I think that's it. A merge. So have you seen or heard about SQL merge? Classic. You can find it in SQL Server and many other databases. All right. So what I'm doing right now is I'm forcing an update against the table, not just adding new records, because adding records are just dropping an additional parquet file. Updating the table here means you need to go mark the existing parquet files as logically removed and add new parquet files. And if that stuff is happening like what concurrently across multiple jobs, what will happen is that maybe one of them will commit while the others are still running. So, but if the others are still like just the first one commits fine. The second one, if it tries to commit now, they do something before they commit the JSON file. They check the files in the table and make sure that nothing else like what has written some data, making my original transaction invalid, because I might be updating or incrementing the same records or whatever. If I write my data, it will look like data corruption or this kind of things. If you don't have what in SQL Server, for example, if you don't have locking, you can find bank transactions. Someone is depositing here and the other one is deducting or whatever, and maybe your conflict. Okay, so if you have concurrent updates touching the same files, you will get errors like this one, concurrent append exception. Append here is not really related to the merge statement. Append because it means like new files are written after like what I pull the data to update, meaning like the data I pull to update is not latest. Someone else has already like what committed some data and my transaction does not make sense anymore. Okay, so if you have concurrent updates, you will find that one of them will succeed. Let me show you the transaction log right now. This is the initial creation of the table, and this is the merge. We have 4 concurrent merges. One of them just succeeded, and everyone else failed because they are like some new files are being written to the folder after they pull the data to inspect and to update. So kind of it doesn't work. I mean, it has to be failed. Okay. So what is the solution here? Unfortunately, in such case, if you can write your code without like taking into consideration that stuff, you will get an exception. But if you'd like to have your code resilient and just work, if such case happens, you can just do a small retry logic. So try to merge it for each one of them. Try to merge, and if it fails, try to capture that exception. Or there is a bunch of other. Retry once again, maybe sleep a little bit of time. There are some options to do this kind of what they call it, exponential delay or whatever. Sleep a little bit of time and try again. maybe maximum 3, 4, 5 times, whatever, and then eventually you'll get your data updated accordingly. So if you do that stuff, you'll find that with the initial run, you'll see that 3 tasks are kind of failing, and they'll be retrying. After that, 2 tasks are failing and 1 succeeding. And after that, there will be one final task failing, and then after that, that will be retried. Meaning, eventually, you'll find that the transaction log is sorted like descending in time. There will be an initial write, and then you'll find I have my 4 merge statements. Okay, and you can see I think the front. Sorry, where is that metadata column? Look at this one. So the first merge is done in try 0. I mean the first one that is an index. The next merge was done in try 1, try 2, try 3, and so on. So if you have any kind of case where you will find concurrent writers, yeah, you can just blindly maybe don't include this kind of auto retry or whatever, assuming that you have another method of retry, like Databricks, they have an option to auto retry failed jobs certain number of times or whatever. But if not, you can just do this kind of manual retry idea. So this is one hint about ACID transactions and how it works in Delta Lake. Final thing quickly, optimization. Has anyone here heard about Z ordering? No, completely new concept. So, but at least maybe if you have used Parquet or this kind of Hadoop and Hive tables, there's a concept to partition a table. So normally you find data on Twitter or whatever, there will be one folder for each year, and inside each folder there will be per month and day or whatever other type of partitioning. So this will be required if you have queries that is aggregate queries, and they are pulling or filtering data using a low cardinality column like a state or a date or whatever. But if you have a table, think about it like table like what all the driving license records for Australia or whatever, and there is some GDPR requirement to update or select or filter whatever a few records. This is a very high cardinality kind of filter, and if you don't have a method to collect the data quickly and easily, these types of queries will be very slow. So there is one optimization option here called Z ordering. I'll explain it shortly, but before I explain it, delta tables, when you add some files into the table, go to VS Code. I mentioned the idea of add protocol action. So it will contain the file name and maybe size and creation date or whatever. I didn't include that stuff in my demo because it was not really required. But when you create delta tables from Databricks or Spark or Synapse or whatever, you'll get this kind of extra metadata, okay? So for each Parquet file, there will be some information about what is the minimum value, for each column, what is the maximum value, number of nulls, and so on. So eventually this information, when a query is issued again as a delta table later, the execution engine like Spark can go and inspect such information without reading the massive Parquet files and quickly find out, okay, it seems that the work criteria is not satisfied, or I will not find any records in this file because the records are completely outside that range of a certain column, vendor ID or whatever. So they use this kind of metadata injected inside the transaction logs very heavily to optimize update queries or select queries. Okay, so let me explain it visually here. So have you heard about New York taxi dataset, NYC taxi? It's very famous. You find it many places. So it's a kind of taxi rides in New York across like a bunch of years. So stuff like what pickup location, drop-off location, amount of the fare or whatever, this kind of things. Pretty much around 1.2, 1.5 billion records, right? And let's assume that we have some queries to filter for certain specific records happening in a certain location. So out of 1.2 billion records, we'd like to grab 3 or 4, all right? So I have an initial need just to prepare the data, grab a copy in our own local folders. So where is that? I have the original copy of the table, or a little bit modified copy, or filtered to exclude very or bad data, exclude bad data happening in negative latitudes and whatever. I have the original copy of the table, and I have something called an optimized copy of the table. So what is that? have an idea called optimize. So optimize will collapse files into big ones if we have lots of small files, but it can also do something called Z order. So Z order means grab all the records that share similar latitude and longitude or whatever and put them in the same file. Okay? So think about it visually. If it was a single dimension, it will partition your data range into equal slots and put every individual slot into the same file. If there's a two-dimensional space like this one, it will grab all the records happening maybe in a rectangle or whatever and put them in the same file. All right? So let's have a look on I mentioned the idea of what the add protocol action. Sorry, it's too big. But I'll be using here in this notebook some Databricks library called Mosaic. It's used for geospatial analysis, and it has also an integration with another tool called Kepler for visualizing maps and so on. So quickly, where are we? A little bit too much code, but this code is inspecting that JSON file. Remember this JSON file? We have, okay, cool. We have lots of files for the original table and the optimized table. The original table is maybe 64 files. The optimized table is a little bit more for reasons, but I have a small snippet to inspect this kind of JSON snippets and come up with something like this one, with this output. So for each table, I can show the path and the size, but I can grab the minimum pickup, minimum latitude, longitude, and stuff like that, and represent that data into something called what was that? WKT, well-known text representation of a polygon or whatever, all right? And then I can use this kind of library called Mosaic to display or render rectangles. So every record here represents a file, all right? And then the rectangle will represent the area covered by the records in that file. It will be kind of top left and bottom right stuff. All right, let's go scroll down. Scroll down from here. Look at this is New York City. And you can see here, look at this one, these are the 64 files, but all of them are kind of spanning the whole region. Meaning like every file will have records scattered everywhere. So if I need to filter for anything like happening here, I will have to read everything, okay? Let's have a look on the same stuff, but from the optimized copy of the table. Okay, I'll go there, scroll down. It looks very similar, but I'll show you one thing. There will be a bunch of outliers, like big rectangles, but if you zoom in here, you'll see the cool stuff. So every rectangle is a file, okay? Meaning that every single area will be covered by maybe maximum 2 or 3 rectangles. You can feel like, so remember this is a rectangle here, covering this kind of spatial area. And there's another file containing data overlaid. So, but all in all, if you have a few records in this place, they are covered by how many files? This one, and potentially, maybe I don't know this. Anyway, but you can feel that from the picture here. The idea is that you grab all the records that live together on this kind of at least geospatial coordinate thing and put them in the same file. So what is the impact here? Let me show you a query against the plain table. So if you query, this is what I'm talking about, the high cardinality query. Query that is like a needle in the haystack, all right? So this one, it will take like 4 minutes. I have to work as not a very big cluster, but still like too much time to wait for that, compared to the 0.7 seconds for sure. Okay. If you go and inspect the stuff here, I'll show to you quickly, very quickly. Okay. This is the cluster is terminated. Anyway, maybe I took more than half an hour and it has been terminated. But the point, I'll give you an idea. Maybe the logs are still there. Okay, cool. So this is the other query, which is, look at this one, 4.76 seconds, filtering data from 1.2 billion records. This is much faster. The cool idea here is that This query is using a Z-order optimized data, which is this kind of intersecting rectangles and so on. Look at this one. It's scanning a folder with a folder containing a bunch of parquet files. Look at this one. My table has 216 parquet files, and it has read one file only, and pruned like ignored 215. So that's why it is super fast. It's pulling data from one single file, and that's why it's loading in memory 5 million records only. Otherwise, it has to load 1.2 billion records, and eventually, quickly that can be done quickly, and you can get your 4 records very fast. All right. So this is one of the optimization things that you can do in your Delta tables that will make them very fast, not only for select transactions, but this thing is also very, very fast if you are doing an update or merge or whatever. Okay, and that's it pretty much. Just maybe one single slide. Most of these ideas, DML, ACID transactions, and so on, cover hopefully during the demos and stuff like that. There are some other ideas related to batch and streaming workloads and schema enforcement, because if you have a parquet table, plain parquet table, hundreds of files or thousands of files and folders, to get the schema for that table using Spark or whatever tool, the tool will have to enumerate all the files and read the header or footer of every file to find out the schema, because some files a file can contain 10 columns, another file can contain 11, so stuff like that. But Delta is much more powerful related to such aspect, because it can bring everything from transaction log very, very quickly. And if you would like to play with stuff, here's a QR code for the whole thing, a bunch of notebooks and stuff like that. And nothing really, just create a Databricks community edition. Is free, and run it should run. Some of them will take a little bit longer on community edition, but yeah, no dependencies here. So yeah, that's it pretty much. I mean, Delta is good. You can use Parquet, but usually in serious workloads in the cloud or whatever, Delta is the way to go. And there, by the way, there are other options, although I didn't quite compare which one is better. Although Databricks claiming Delta is superior, we have Iceberg and we have Hoodie, I think, right? Cool. So I think hopefully I'm not too much over time.
No, that's cool. Any questions? Why would you pick Iceberg or Delta Lake?
Look, all of them are open source, really. For me right now, if I'd like to be pragmatic, or I'm not really biased to Databricks or whatever, I can, and most of them are simple. Take your workload, try it here, try it there, and just test for yourself. Yeah. Depending on your priority. So maybe your priority is your storage format should be accessible from lots of other tools like Power BI or whatever. So test again is this kind of priority or factor. If your factor is maybe storage, maybe some of them will be saving you storage cost more than others. So, yeah, just be pragmatic, and for sure every vendor like in Databricks and the guys from Iceberg or whatever, I think they are from Netflix, they will come with benchmarks. Databricks claims right now Delta Lake is the top, but yeah, if you don't trust this or that, test for yourself. Yeah.
Thank you. Other questions?
Sorry, just because I'm not familiar with Delta, can I run a portion of my workload in Delta using the Delta paradigm?
Okay.
Or is it
Come again, please?
Can you run just a portion of your data lake using Delta, or is it like really an all or nothing approach?
No, it can be a portion of your workload, really. So most of the time, especially on Azure Data Factory or Fivetran or whatever, you will ingest the data into a raw layer using maybe C3 or Parquet format or whatever, and then after that it will be pulled from that raw layer into the medallion architecture, if you have heard about the bronze and silver layer. So initially the data will be coming usually in non-delta format for sure. So and then, but yeah, you don't have to use it for all your workloads.